All right, so let's get started. Welcome back after the long weekend. Today we're going to talk about language modeling, which is basically the core NLP task that we're going to spend most of the semester on. Today we'll introduce the task, how it's set up, and go through some very simple models for solving this task that rely essentially on counting words and normalizing them to get probabilities. Next week, we'll look at more complicated versions of these models that are implemented with neural networks and have actual trainable parameters. And then the rest of the semester will just be building on the complexity from there. Okay, so before I get into it, last time I was ignoring a lot of YouTube comments. So today, and potentially for future lectures, my postdoc, Marjana, is here, and she will be monitoring the YouTube chat box for me. So if at any point Marjana decides that there is a question worth answering at that point, she'll interrupt and ask it. So for those of you, let me see how many people are on YouTube. 4. That's 4 people of you. You have that, whoops, oh, sorry, this is, okay. So before we start with the task, there were some questions in the anonymous form. Someone asked, do class projects ever get turned in? We've done this class for a couple semesters since I've been here, maybe like 4, and there have been a couple papers that come out of these final projects that get published at some at conferences and some at workshops. It does require a lot more effort on your part after the class to actually turn it into something like the ones you'll be reading for homework 0, but yeah, it happens. Another question, can I choose a simple paper for the homework 0 paper review? I'm not actually sure what simple means here, but as long as it is a published paper at one of those 2 conferences, you can choose it. So yeah, I guess everyone's definition of what is simple is different. And someone said the homework 0 deadline, which is I think Monday, is very soon. We haven't actually learned anything to help us do it, which is a fair point. However, after this lecture, some of the answers for the homework will even be in this lecture, so if you're paying attention, should be pretty straightforward. I think the only thing that might take time is if you are unfamiliar with Python and PyTorch, and there are a couple questions that involve looking through the documentation and trying to figure out how to implement certain simple functions. So if you haven't started the homework and you are not familiar with those things, I would highly encourage you to do so early. But this is not a homework that we expect should take a huge amount of time. So I think it should be fine. All right, any other logistics or non-content related questions from anyone? Anyone in the YouTube chat? All right. Okay, so let me just step back a little bit before we start talking about the task and explain again why we're focusing so much on this task of language modeling. Because it's not super clear from your readings. How many of you did the readings? All right, that's about what I expect, like 5. Okay, so maybe it's irrelevant to reference them. So anyway, this is what I was talking about last lecture with the difference between supervised learning and self-supervised and transfer learning. In the past, I would simply, if I wanted to solve this task of sentiment analysis, take a labeled data set of movie reviews or something that I crawl from IMDb or Yelp, and I would just train a model from scratch on that data, and I would get a sentiment model. So of course we'll talk more about what this whole process looks like, but at a high level, this is what it was. I start from nothing, then at the end I have a model that can do sentiment analysis, but it's also learned all its knowledge of language comes only from this fairly small data set of labeled reviews, right? Because even if IMDb has hundreds of thousands of reviews, that's still a relatively small amount of text compared to like the entire internet, right? Or any sort of huge corpus of text I could get. So nowadays, we use a variant of transfer learning to solve basically all NLP problems. So this proceeds in two steps. First, we have a self-supervised task, which, if you remember from last time, I can get free labels from just through the text, right? So this task of predicting the next word, right? Or predicting a masked word. I don't need anyone to annotate data to get me training data for this task. So I get a huge amount of unlabeled text, and I train a massive self-supervised model. So in this class, we'll be focusing mainly on language models and masked language models for this step. And so I get a model that becomes very good at predicting the next word, right? And like we talked about last time, this model has learned a lot of properties about language, right? Just through this process, as we'll see later on in this class. So I can take this model and then, using my small amount of labeled reviews in this case, I can fine-tune this model to specialize it to solve this sentiment analysis task. So the big difference here between this and this is that in this transfer learning setup, we are not asking the model to learn everything it needs to know about language just from these IMDb reviews, right? Instead, we've given this model as much unlabeled text as we want to have it learn basic linguistic concepts. And then this second step is essentially just to get it to focus on the task that we care about. So this version is way better than the purely supervised version, as we'll see over and over again in this class. Not in this lecture, but in the rest of the semester. Okay, so then we should talk more about how this model actually gets trained, right? What is its training objective? And language modeling, or the task of predicting the next word, is going to be the most dominant approach that we will look at in this, this semester. There's also a variant of this, which you could argue, reasonably argue, whether it should be called language modeling at all, called masked language modeling, where instead of predicting the next word, I will give you some amount of text and mask out a word or multiple words in somewhere in that text. Not necessarily the next word, but it could be in the middle, and then ask the model to predict the missing word. So in this case, it's a similar task, right? It's still predicting a word. I have infinite data from the internet or whatever sources, because I can easily just randomly mask out words and then ask a model to fill them in. But it learns slightly different things, right? Because in the second setup, I have information from the past and from the future. For our language modeling task, which we're going to look at today, I only get information from the past, right? The previous X words predict the next word. All right, so in this formulation, language models assign a probability to a piece of text. So this is one of your homework questions. Why would we ever want to assign a probability to a piece of text? One important use case is in machine translation, right? So maybe I have two competing translations from the same source sentence. I flew to the movies and I went to the movies. And my model is kind of confused between these two. It assigns an equal probability to both of them, my translation model. So one thing I can do is take a language model that's been trained in, say, on English text, and ask it which of these two sentences is more probable, right? And no one, I presume, would ever say they flew to the movies unless, okay, I mean, like you're super rich, I guess, and you fly everywhere. But I went to the movies, much more common, right? So maybe this should be the translation that's chosen. Similarly, in speech recognition, right? I get some sound signature as input, and I need to convert that into text, right? So I saw a van versus I's of an, those sound very similar. But of course, I saw a van is much more plausible to hear than whatever this is. So these are two examples. For those of you who have done the homework, which I'm not sure, based on how many of you did the reading, it's pretty pessimistic about that. But anyone else have any other ideas of where this is potentially useful? What's that? Oh, yeah, sure. Checking grammar. So services like Grammarly, for instance, although we don't know what they're actually using under the hood, they're most likely using language models to do some part of this correction. So why exactly would you want the probability of a sentence in? I see. So maybe like some sort of stylistic information about the particular email or something. Yeah, so there are multiple use cases for this. And setting aside the utility of a probability of a piece of text, language models can also generate text. So we'll talk about that later today. But every time you use autocomplete, for instance, this is a language model under the hood. Google search, right? The autocomplete is using language models, and actually their ranking of their search results now is also using a huge self-supervised masked language model. So the autocomplete and the actual search itself are both relying on these models. And Google Translate, for instance, is using huge neural language models. So almost every service that you see commercially that is related to NLP is using one of these models in some form or the other. Yeah. Yeah, certainly in question answering. So we'll see later in the semester how all of these tasks can basically be reduced into a very similar or even the exact same framework and be solved with a language model. So it's kind of interesting to follow the historical progression of all of these tasks. So something like question answering and, say, machine translation were completely separate. The approaches that were used, you couldn't apply, say, a QA model for translation or vice versa, even like 5 years ago. But now everything is kind of converged, so you have models that are capable of doing QA, translation, sentiment, all within the exact same model. So it's pretty cool, and we'll get to that a lot more. We just have to work our way through the basics first. All right, so the task more formally of language modeling is given some sort of, so you can frame it in a bunch of ways, but you might be interested in computing the probability of some piece of text, like a sentence, like all the examples we just talked about. But we can also frame this task as predicting the next word, as in autocomplete. And a model that does either of these things is called a language model. So we can see that if we have this example phrase, its water is so transparent that, we can compute the joint probability, the probability of this phrase, by relying on these conditional probabilities of probability of word X given all the words preceding that word. And this is just a basic application of the chain rule of probability. So if you remember the conditional probability, this is all like basic stuff, so you should catch up on this if you're unfamiliar with this. But essentially, the chain rule will decompose this joint probability into the product of multiple conditional probabilities. So P of A and B and C and D is the product here, P of A times P of B given A, P of C given A and B times blah, blah, blah. So when we switch over to actual text, right, it's much the same. The probability of the sentence, word 1, word 2, blah, 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 word n, is the product of these probabilities of word sub I given all of the words, word sub 1 to word sub I minus 1, right? So going back to our example, the probability of its water is so transparent is the probability of its times the probability of water given its times the probability of is given its water, blah, 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 right? And so if we have a language model that is computing these conditional probabilities, we can always use it to compute the joint probability of any given input text. So when training these models, which we'll look at next week, the neural versions of these models, we set it up such that the training objective is to predict the next word given all of the previous words. And we might use that model after training to compute joint probabilities if we want to. Okay. And in the terminology of homework 0, this part, all of the words that we have observed up till this point is referred to as a prefix. And we'll be using that terminology for the rest of the semester. Okay. So how can we estimate these probabilities? Let's say I have a big training corpus, right? And I'm interested in the probability of the given its water is so transparent that. So I could easily just count up all of the occurrences of its water is so transparent that the, and then divide that by the count of the prefix, right, to get this probability. But what are the downsides of doing this? I see what you're saying. So you might say, its water is so transparent that is a very specific prefix. And it's very similar to, I don't know, its surface is so transparent that, or it's a liquid or whatever. And maybe we want to share some probability among all of these related, semantically related prefixes, right? So this is a big issue with all of these count-based models. And we will address this, this problem next week. But there's a more fundamental issue here, right? The fact is that how often am I even going to observe this particular prefix or this continuation? I would just need an insane amount of data. I mean, this is related to what you said, right? I may never see enough data for estimating the probability reliably, right? And so maybe, it does happen that if you train some of these count-based models on huge, like billions or trillions of words of text, then you can get an accurate probability, perhaps. But language is creative, right? I could easily form a sentence that has never been said before, and a model like this would struggle, right? Because it wouldn't have observed that in its training data. So the way that Engram language models work, which is the simplest type of language model, actually there are simpler types which are kind of ridiculous, and they're just for toy examples. Maybe I'll talk about that later if we run out of, if we have time at the end. But commonly in Engram models, we apply what's known as a Markov assumption. So we're just going to chop off some of the words in our prefix, and this makes it more likely that we will observe the prefix in our training data. So the probability of the given its water is so transparent that, we will just simplify this to the probability of the given that, if we're using a bigram model, which is only considering the immediate preceding word in the prefix. This is obviously bad, right? If we do this, we are ignoring the whole like water thing and the transparent thing. There's so many fewer constraints when we remove everything except the previous word that. Maybe we could do a little better if we include the previous two words, right? So this is a trigram model, the probability of the given transparent that. This is still kind of strange, right? Like, I don't know the entire subject here, the water. So my estimates are probably not going to be very good for this specific case, but maybe it's much more likely that I'll observe more examples of transparent that in my training data. There's also a question of space. How much space does it take to store all of these counts? which we'll get into in a bit. So as we increase the number of words in the prefix, we're storing exponentially more counts, and this makes us run into memory issues. So applying this Markov assumption, we simplify each of the conditional probabilities in the chain rule. So now you can see that k here is the number of words that were going back in the prefix. So from the previous, from this equation, right? See, we were starting at word 1 and going up till word I minus 1. And if you imagine we're doing this over like a huge book or something, potentially this prefix could be thousands or tens of thousands of words long. So here, if we set k to 2 or something, right, this prefix will always be like 1 word long. So we're no longer having to store all of these counts. Okay, so this is obviously pretty straightforward. It's kind of just a hack, right, to be able to estimate some sort of probability for these various prefixes and continuations by simply counting. So we could take the simplest possible case where we consider 0 words from the prefix at all. So as you can see here, the joint probability, if we assume this unigram model, which is considering no words from the prefix, is just the probability, the product of the probability of the words individually in this this sentence. So what is a downside of this model? Yeah, so you can see that in this example here, right? Look at the words that are being generated. And of the, right? These are words that occur most frequently, so they will have the highest probability if you don't consider any sort of prefix. And the model, this is still not terrible. I mean, it is terrible, but it's at least more intelligent than just completely choosing at random, right? Because it is true that those words occur more frequently than other words, and so, yeah.
Okay, why isn't it going to this thing?
This depends on the way in which you're generating text from this model. So actually, this is a good question, the question in the yellow. So yes, one way we could do this is, well, let's just say the is the most frequent word in our data set. If we do what's called greedy decoding, I'm just going to produce the highest probability word at every step. And so with this unigram model, since it doesn't rely on any words that I've produced in the past, right? It's always just the current word. The probability distribution is not changing depending on what the prefix is. I would just produce the if I pick the argmax here every time. In general, we don't use this approach to generate text because it lacks diversity. There's all sorts of other issues with it. It runs into degenerate cases. It repeats itself over and over again. We'll talk a lot more about this at some point later in this semester. What's an alternative way to generate text from a language model that maybe does not have this issue of just producing the same word over and over again? What's that? So if I remove stop words, there will still be one word that's more frequent than all the other words, which I'm going to keep producing, right? So there's maybe another way. Exactly. So I could sample from the distribution instead of just choosing the argmax and sample based on the probability of the word. And that's how you can get something like this, where you can see that the words are different every time, but we're sampling these words by their, essentially their frequency. And so that's how you see N of all these stop words occurring more often than other words. Just to clarify, for those of you who are unfamiliar with the term stop words, I guess the term arose because these are usually words that you try and remove from your data, or at least in the past you used to remove, because they're kind of uninformative. If you're interested mostly in words that have a lot of semantic content, right? So here maybe I'm interested in dollars and quarter and transparent and water in our previous example, not so interested in that or and. Nowadays, we usually keep stop words in because they actually serve an important function, obviously, when we're understanding language, right? They're necessary to make sentences grammatical and easy for humans to understand. So yeah, this is another kind of change between how NLP used to be done even like 5-10 years ago and how it's done now. Okay, so we'll also look into more complicated sampling algorithms later on in the class after we go over more powerful language models. All right, so the reading had this interesting example, so this is clearly new to everyone here, where you can see the effect of adding more and more words from the prefix into your model. So this 1-gram, a unigram model, oh, sorry, I guess this is is this grammatical? It's hard to say. I don't know if 1-gram here is referring to the prefix size or the... this looks pretty bad, so I suspect this is a unigram model. But you can see that as you increase the length of the prefix, the outputs from this model get better and better. So, I mean, they don't make sense too much, but they at least start looking more like real sentences. So like here, King Henry would, I will go seek the traitor, a great banquet served in. I mean, obviously it's not coherent at all, but it's kind of following basic grammar. And you know, you can get to this point by only considering the last 3 words in your Engram model, and this is estimating the counts just from Shakespeare's plays. So pretty interesting. So nowadays, we have neural language models that can theoretically handle thousands of words of context, not just the last 3. However, it's a little unclear how much they're actually using the information from thousands of words away and how it even should make use of that. So that's also something we'll talk about more in later classes. So, of course, we can just arbitrarily keep extending the number of words in our prefix to whatever we want, but we run into these efficiency issues, right? We can't store the whole count table in memory after some point. Also, it's just not a great way of dealing with long-distance dependencies, right? So here's an example. The computer, which I had just put into the machine room on the 5th floor, crashed. So here, like, how many words back do I need to go before I see the actual thing that crashed? Computer, it's like, what, 12 words or something? So if I don't have a 12-gram model, at least, I'm not going to be able to know, like, what is the thing that crashed. So yeah, this is obviously a very limited formulation of a language model, but still, it has been useful for probably 20, 30 years before. I mean, it's still useful, but not so much now that we have these new neural network language models. All right, so maybe I'll pause here. Any YouTube questions, Marcelo? No? Any questions? Well, it's hard to say, right? So imagine you're reading Harry Potter, right? So of course, like if I am reading the book and I just start at chapter 2, I'm going to miss a lot of crucial information, right? Even if I read the rest of the book, there are things that happened there, you know, potentially thousands of words ago that would have set up some character development or introduced some events or terms or entities, you know, all of that kind of stuff. Of course, it's not like you can remember right now what is word 732 in Harry Potter, right? But you probably created some sort of higher level, like abstract representation of the important concepts, characters, events of the story. And that's what we are, I mean, no one really knows what humans are doing, right? But they're certainly doing something, forming some sort of representation. And it's definitely not the case that anything past the last 20 words is useless. You can just think about how you read a book and you can easily see that that's not true. It's hard to port over any sort of hypothesis we have about how humans process long-term dependencies to to these models, as we'll see later on. Oh, okay. Do you want to read it?
Instructions to models like GPT use a certain length of words for predicting. For example, in a conversation, would they keep all attention weights from frequent to low?
Yeah, so the question is referring to the OpenAI model GPT-2, which we'll talk about in a couple weeks. This is a big neural language model. And the question is, do models like that also have a fixed limit on how many words in the prefix they can process? The answer, not only for that model, but for basically all neural language models, is yes. The prefix length is much longer than this, right? GPT-2, I think, is like 1,024 words, or tokens, rather. Some of the bigger models these days can get up to like 8,000 tokens, which is, pretty long, but still not covering an entire book. And as we'll see, the methods for scaling out these models to such long sequences are kind of primitive right now. So we need more complicated things before we're going to be able to actually use the information in these contexts. Okay.
Is it well known how human brains possess long-term dependencies in a language? And are there many models that are biologically inspired?
Well, you may be more qualified to answer that than me. I don't know. I assume there are definitely models of working memory and short-term memory. I don't know how those relate to reading exactly, but the second question, are models these days biologically inspired? I think mostly no, because we don't know what is going on in our brains, right? So it's hard to be super inspired. Of course, in the terminology of some of these models, we use things like neuron, and those are all biologically inspired, but kind of just like diverged a lot. So it's hard to say that there are like strong analogies. Yeah, anyway, I think we're getting too far outside the point. Let's focus on these simple models for today. So, right, we mentioned, we could just count up the occurrences of a particular prefix plus the next word and then normalize it by the count of the prefix, and this is how we can get a probability estimate of some particular bigram. So this process formally is known as a maximum likelihood estimate. So we estimate all of these conditional probabilities from the counts that occur in some corpus or some data set. So for example, actually I probably do have an example. Yes, okay. So this also was in your reading, but let's say I have just a corpus of 3 sentences. I am Sam, Sam I am, I do not like green eggs and ham. And you also see we have these special symbols. This S here at the beginning indicates that it's the start of a sentence, and then this /S indicates that it's the end of a sentence. So we have these two special symbols, and then we have these 3 sentences. So if I wanted to get the maximum likelihood estimate of, say, probability of I, given that I've seen the start of sequence symbol, well, all I have to do is count up first, how many times do I observe the start of sequence symbol? I have three cases here, they're all at the beginning. And how many times does I follow the start of sequence symbol? So 1 time here, not here, and again here. So I have 2 of the 3 cases, and so this probability is 2/3, right? It's easy, we're just counting and then dividing by another count. Let's do an exercise. What is the probability of Sam given the start of sequence symbol? What's that? Okay. I assume everyone said 1/3. It is hard to hear. So Sam given am then, right? I'm going to look up how many times am occurred. There's only 2 occurrences. And how many times was it followed by Sam? 1, so it's 1/2, right? This is like a 2nd grade classroom here. So in this way, I can estimate all of the conditional probabilities that are necessary to fully specify this bigram model. And then I can just sample from it to generate new text if I wanted to. So another thing for homework 0, and in general for all of NLP, is you should be aware of the distinction between word types and word tokens. So word type is a unique word in the vocabulary. So for example, I am Sam, the start of sequence symbol, the end of sequence symbol, and then do not like green eggs and ham. These are the unique words here that form my vocabulary. So a token is any occurrence of a word type in the corpus. So I here occurs 3 different times. So there are 3 separate tokens that are exhibiting the word type of I, right? So you can imagine a type is an entry in the vocabulary. A token is any instance of that type in an actual data set. So I'm going to have more tokens than types, right? Because tokens I can have like duplicate the same word type. Does that make sense? Yes. It depends on if you do say something like stemming. I don't think anything here would get stemmed. But let's say I don't know. I have never liked green eggs and ham, right? So maybe that word liked, which is in the past tense, if I apply a stemmer, I might want to just normalize that to like and get rid of that suffix. If I apply stemming or lemmatization, I'm going to count the types and tokens after that process has happened, not before. So that liked would be the same as like or liking or likes or whatever. Again, in general, these days, things like stemming are rarely used compared to even a few years ago, and they're used only for certain applications. But we generally we try not to deviate from the raw text as much as possible when we're working with the newer models. That's a good question. So this model doesn't deal with that at all. It treats, so let's see. So let's say the word bank, for example, right? It could be a river bank, or it could be a financial bank, or it could be, there are many senses of bank, right? In this model, there would be one word type for bank, and all occurrences of bank would be treated as tokens of that single word type. This is not good in a model like this, right, where you might want to actually distinguish between these different senses. There are ways that you can instantiate a different entry in your, like, these probabilities for every word sense, but it's actually quite difficult to figure out within any given context which sense of bank is being used. So yeah, in the newer models, we don't do anything like this, although it's actually a good question because some people, I think, are exploring whether adding this word sense information into these big neural models will be helpful in any way. So I don't think there's any research yet on that, but people are actively working on it. All right. Oh, yeah. Sorry, I didn't hear the last one. Oh, the order. Yeah, so here we just have a bigram model, right? So we're only looking at the immediately preceding word. But if we had a trigram model, so we're looking at the past 2 words, then I would have a prefix like amsam, and then ask what comes after amsam, right? So I'm always considering the order of the words within the prefix when I'm estimating these probabilities. No, because like amsam is going to be a different occurrence in your probability count table than sam-am. Sam-am actually never occurs here, so. Oh, you want them both to be used. No, because the count for both of these things is different, right? So let's say I have a trigram model. So when I'm scanning through this sentence, I have start of sequence I have I have Sam, and Sam end of sequence symbol. So I add a count for every prefix here. So given Sam, I observe the end of sequence symbol. But that's different than given Sam, I have not observed this, right? So the two counts are different. Yeah, I guess it's unclear from this example because we're only showing a single word in the prefix, but the order of the words in the prefix is important. Yeah. Yeah. Oh, that's a good point. Yeah, so you need the end of sequence symbol. I don't, not sure if you need the start of sequence symbol or not, especially in training these newer models. I don't think you do, but yeah, the end of sequence symbol is necessary because the model needs to know when to terminate, and you need it to get a valid probability distribution. All right, so let's look at a slightly less synthetic example. So this is from a data set of sentences about restaurants, I think restaurant reviews. So you can see some examples of the sentences here. I'm looking for a good place to eat breakfast. Mid-price Thai food is what I'm looking for, blah, blah, blah. And I want to train, again, a bigram model in this. So what is a process? First, I'm going to form this table, which I'm going to use to keep track of all the counts of things that I observe in the data. So here, these rows here are the previous word. They correspond to the prefix. And then these columns are the current word, W sub I. So you can see here the count, the number of times I see the word want after seeing I, 827. The number of times I see food after I is 0, right? So and obviously this is just a small subset of what this table actually looks like, right? Because you can imagine how many word types, unique word types are in the data set like this. Probably a lot, right? There's a lot of unique restaurant names, food names, blah, blah, blah. So this table might be, like 100K by 100K or a million by a million. So you can quickly see the scaling problem, right? So, okay, anyway, let's say I have these, this is just, again, a subset of this table. Let's say I do these counts from the whole data set. Now, to get my probabilities, I'm just going to divide by the unigram, because it's a bigram model. So I'm going to just divide by the unigram count. So to get the probability of want given I, or let's say lunch given eat. So what's the probability of lunch given eat? I'm going to take the number of occurrences of lunch given eat, which is 42, and I'm going to divide that by the total number of occurrences of eat, which is 746. So 42 divided by 746, I assume is 0.056. And you can similarly do this for all of the entries in this table and get these probabilities. And this table here of all these probabilities, these are the parameters of your bigram model. So you've estimated these using the maximum likelihood estimate. You're just counting and normalizing these tokens in your data set. And I can now proceed to use this however I want. I can sample new text from this model, or I could use it to measure the joint probability of some new sentences, or so on. So in a trigram model, maybe to help you understand further, these rows here, they would not just be single words, but rather they would be a sequence of 2 words each. So this could be I want to eat, and then Sam and Sam would be completely different rows in this table. So they would have different probability distributions. What's that? Yeah, so this is up to you. This is a problem known as tokenization, right? So we explained what tokens are. Now you need to decide how you even form these tokens in the first place. So in the homework, we asked you to use white space tokenization. So every time I see a white space, I split, and then I assume the thing that's remaining is a token. But of course, that's not the best because of, I mean, someone even posted in Piazza, right? There's, you know, punctuation that's glued on to some of these words. There's contractions. Maybe we want to split those into two separate things. This is an open area of research. What is the best way to tokenize? People these days don't even use words, honestly. They use things like subwords or character level, or as we'll see, even byte level tokenization. So we'll have a whole lecture on this after we cover the neural models, but it's a good question. It can really affect the quality of your model. Yeah. Mm-hmm. Yeah, so this, what you're saying is there's a class of language models that are feature-based. So I can essentially train a logistic regression model or some sort of classifier to predict the next word given some features that I've extracted from the prefix. So this is another way of, that we're not gonna talk about in this class, although I have in the past, we just don't have time this semester, but you could add features like subject computer or something like that to this model. And then you would just hope that it's not sparse enough that the model can actually learn from those features. But yeah, you can get very complicated features involving long distance dependencies. That just requires work from us, the model designer, to know that, okay, well, the subject is obviously very important, so I want the model to consider it. Right, but it gets a little more difficult when you have longer and longer prefixes, right? How should I take advantage of some information 7,000 words ago, right? It might not be as easy as apply a parser. So yeah, that's a good question. You can do things like this. All right. So let's move to one of the issues of these, the models that we've discussed so far. So we form this probability table, and let's say I want to now use it to estimate the joint probability of the sentence, I want English food. So using the chain rule again, and remember this is a bigram model, so we're gonna apply the Markov assumption, we're gonna chop off these prefixes at just the immediately preceding word. So I'm gonna have this product of probabilities here, and I get the number 0.000031. So, and this was only with 7 tokens of input, right? You can imagine if I have a much longer sequence, this probability is going to get smaller and smaller and smaller until eventually I might have to deal with some numerical underflow issues. So what should I do in this case? Anyone have any ideas? Yeah, so instead of considering this as a product of raw probabilities, I can consider the sum of the log probabilities, right? Just using basic logarithmic math. And so now, taking just a toy example, if I had this sentence, I love, 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 love the movie, the probability of this, given some bigram model that I estimated a few years ago, was like 6 times 10 to the minus 7th, so it's quite small. But you can see that by turning this into the sum of the log probabilities, it's much more manageable. So in general, when we are working with the models that we'll discuss later in the semester, we'll always be working in the log space. And the evaluation metrics that we'll be using also take the log probabilities as input. Okay, so let's skip back and look at the raw probabilities for a bit. I had said that language modeling is a good task because the resulting model learns a lot of linguistic properties from the text. And this is true even for a model that's as simple as a bigram model, right? So you could imagine a model that knows that English or Chinese coming after want or want to eat is learning some world knowledge, right? That maybe people want to eat things that are different cuisines or something like that. There's also clearly grammar that's being learned here, right? Like to want or want to, right? There's a infinitive being introduced. Or the probability of want given spend is 0, right? This is ungrammatical, so it would never occur. So I've learned all of these things, even with such a simple model. Also, probability of I being the very first word in a sentence, that happens quite a bit, right? So even the simple model can learn a lot of useful things, and you can only imagine what a more complicated model that's much better at this task of language modeling, it can pick up a lot more things. And if you're interested in using Engram models, say in your projects for anything, because they are computationally much faster than to form these counts. They might be memory intensive, but at least they're very efficient. They require only one pass through the data set to just count and divide. So these are, especially KenLM is a great toolkit for Engram models. Okay, so one thing that we need to talk about is how to evaluate a language model, right? So we saw from qualitatively that a 4-gram model generated much better looking text than a unigram model, but how can we quantify this? How can we quantify that a 4-gram model is actually better than a unigram model? And this is a basic machine learning paradigm, right? I estimate my model's parameters, or I train my model on some data set, the training data set, and then I evaluate it on a separate data set that I've never touched before. The model has never seen it before, and I see how well the model can generalize to this held out data. So commonly we split our data sets into 3 folds. We have a training set, we have a validation set, and then we have a test set. So in a validation set, I might use this to further improve the model that I'm training by messing with various hyperparameters. So perhaps well, we haven't actually talked about any hyperparameters of Engram models, but there's various like smoothing things that we can do that I'll talk about a bit later. I could test all of these algorithms out on my validation set, and then ideally I will only run my model one time on the test set to get the final score. And then I can compare that number to any other language model that's been trained on that same training set. So we need some sort of evaluation metric that tells us how well our language model is doing compared to another language model. So what intuitively is a straightforward way, if I have a training data set and a held out data set that the model's never seen before, how could I evaluate 2 different language models and decide which one is better given the held out data set? Yeah, exactly. So language models give you the probability of a piece of text, right? So assuming that the held out data set is like normal grammatical text and not just random gibberish, then a better language model should assign this a higher probability than a worse language model, right? And we already know how to compute the probability of some piece of text using a language model, just using the chain rule. So this is a good evaluation metric, right? And intuitively, this is what we want. However, in practice, we actually use a different metric, which is just a function of the probability of the held out data. Yeah.
This is going to sound like a very, very question. How do we generate good test value?
How do we generate good gibberish?
Yeah, so like there's only one test probabilities of real sentences, right? We also want to see if there's like flukes and want to have some gibberish sentences, which ideally language models would generate low probability sentences, right?
But are grammatically correct?
That's
well, like why?
question.
Otherwise, why would you want a language model to give you a high probability for gibberish?
No, but what I'm saying.
Oh, you want it to give you a low probability.
Yeah, like a good language model on a test set, you have a bunch of gibberish sentences, right? And if it gave a high probability of those being good sentences, that's bad language.
You know, this is actually not a bad question. It's actually a great question because some of the really good language models we have now they do a good job of assigning high probability to real text, but they also assign high probability to like not complete gibberish, but like text that is not related to the prefix or has some degenerate, like it repeats itself or some weird cases like that. It's actually an active research area of how to make language models better at distinguishing these cases from real text. So that's a good point. But it's also hard to get examples of these things. Like you could put, I suppose you could make a gibberish data set and then evaluate your data set based on it, but it can't just be randomly selected words, right? You would need some sort of function to like make intelligent gibberish, maybe like a little bit of repetition, or we'll actually talk a little bit more about some of these approaches later on in the class, but yeah, not a dumb question at all. Yeah. Wait, sorry, can you say it again? Yeah. I mean, the general assumption is that if the held out data is, let's say, so some common benchmark data sets are like Wall Street Journal is a very popular language modeling benchmark, or Wikipedia, for instance. So you train on, say, 100,000 Wikipedia articles, and then you evaluate on 1,000 that you've never seen before, something like this, right? But you know that the held out data set, these are legitimate Wikipedia articles. They've been written using proper English. They are generally coherent and relevant to each other. They're not gibberish, right? So in this case, you want a model to know all of that, right? And know that this text should be high probability. Obviously, you don't know what exactly that probability should be, but the assumption is that a better model should assign a higher probability to this naturally occurring text than a worse model. Yeah, so yeah, I mean, your held out data set is obviously a very limited picture of all possible sentences, right? But if it's large enough, it's still, I mean, you can see, we'll see later on, like some of the huge differences between some of these models on even a small amount of held out data. So obviously it's not perfect, but you can't be perfect in this case. Okay, so, yeah. Oh, what did this slide say? Right, so evaluation sets in the three folds that I mentioned, train, validation, and test, you estimate your model parameters, in this case that probability table, just from the training set. You can use the validation set or the test set to evaluate the model. The purposes of both of those is different, right? The validation set is used to improve your model until you're confident you've done all you can in tuning its various parameters. The test set is only used as one time to compare with other models that have been trained on the same data. So test and validation are I'm referring to. Oh, yeah, I don't know what that is. I assume it's one or both of those. Maybe they're referring to the test set.
And there's also say for 2 seconds
Okay, wait, but the person's on YouTube? Are they in the class right now? Okay, I will be here for a few seconds after that. Okay, so just to be a little more clear, one potential example of this is I have a bigram model. I estimate that probability table from a bunch of New York Times articles. So I get this table, and then I evaluate it on Washington Post articles, right? So one important point is that there should be no overlap between the training set and the validation or test set. Why is that? So what if there's like half the sentences in the test set occur in the training set? And so what impact would that have on, say, the model's estimate of the probability of the... Right, so it would assign a much higher probability than otherwise because it's already seen all the statistics of those sentences before. It's encoded them in some fashion in this table. Those probabilities are going to be, quite high, and the resulting estimate is essentially useless. It's measuring how well the model can copy the training data. So, right, we don't want any overlap between the training set and the test set because of this. And this is not only true for language modeling, but also in general for any machine learning task. Unless you're doing some very simulated experiments or something like that, you never want any leakage between the training set and the test set. So we have had people just not have a test set or a validation set before in their projects. I'm just going to say this now. Please don't do that, or you will lose a huge number of points. So, yeah, you don't want to do it on any task. Okay, so in the last 15-ish minutes here, we'll look at the evaluation metric that is a standard for language models. As I mentioned, we can obviously measure the raw probability of the held out data set. But for various reasons, we use a function of that, essentially the exponentiated version of that, which is called perplexity. It has some interesting connections to information theory, which make it perhaps a little more intuitive. But in the end, the intuition is the same. Like a model that assigns a higher probability of the held out data is better than a model that assigns lower probability. So, how does this work? Well, let's just say I'm working with raw probabilities now, not log probabilities. We'll see that on the next slide. Perplexity is just the inverse probability of the test set normalized by the number of words. So that's also important because let's say I don't normalize by the number of words in the held out data set, then the probability of like a 50-word held out data set is going to be much higher than the probability of a 5 million word held out data set, right? Because I'm just multiplying more and more and more probabilities together. I might instead want a length normalized metric that can be comparable among these various things. So I might just normalize by the length of the held out data set. So that you can see we're doing in this. It's perhaps more intuitive in the log space. But yeah, we're essentially doing this for historical reasons, and just to demonstrate the intuition, let's say that I have a vocabulary of all of the different digits, the 10 digits, and I have a sentence that is just randomly constructed with, I just randomly choose a different digit with probability 1 out of 10, so 0.1. So if we look at the perplexity of this model, which it doesn't know any better than to assign 0.1 probability to every digit. This sequence, digit 1 to digit n, each of these probabilities is going to be 1/10, and the total probability is 1/10 to the n. When we apply our perplexity computation, so we exponentiate by -1 over n, where n is a number of digits, we end up just getting 10. And so this is telling us essentially the branching factor of this model. So at any point in the sequence, it has 10 equally plausible options to predict the next digit, right? Because this model doesn't know any better. It just thinks that all digits are equally likely. So the perplexity of the model is 10, meaning and the size of the vocabulary is 10, meaning it's essentially clueless about this model. So if the perplexity were lower, right? If the perplexity were 1, or if something very low, that would indicate that the model has extreme confidence in what the next digit is going to be. So perplexity, as it gets lower, the probability of the held out text gets higher. And so we want a language model that has the lowest perplexity possible, as it has the least uncertainty about what is coming next. That's essentially the intuition. So when we're using log probabilities, this is going to be what you encounter in practice when we're looking at these more complicated models. We have the sum, right, not the product of the raw probabilities, the sum of the log conditional probabilities. We're normalizing by the length of the held out sequence, where n is the number of tokens in the held out data, and we exponentiate. And importantly, this might not make sense now, but what is in this exponent, what is being exponentiated here is a token level negative log likelihood, which is actually the objective function that we use to train neural language models. So we'll come back to this next week, but it makes it very easy for us to compute the perplexity of a model, given that we've used some standard neural network libraries to train it. All we have to do is exponentiate this is also the cross entropy loss. We just exponentiate that and we get the perplexity. Okay, and going back to someone's question here, this is an example of language models of different orders. So order here refers to the length of the prefix, also the N and the Engram model. And it's been trained on the Wall Street Journal. So there's some articles that were reserved for training, different articles in the test set. You can see 1.5 million words in the test set. And you can see the perplexity of a unigram model, a bigram model, and a trigram model. You can see how it keeps falling as we add more and more words into the prefix, which indicates that the model is getting better and better. Nowadays, for benchmark data sets that we have, perplexities on, say, Wikipedia are quite low, maybe like 15 to 20. There are obviously more challenging data sets and domains out there. So you can't really compare perplexity across data sets, but within the same data set, you can compare different models based on their perplexity. Yeah. What's the perplexity of a person? Oh, I see. That's a good question. I don't know I don't know how you would measure that, right? Because you need access to the full distribution. Like, a person is not forming a full distribution over every word that they know before they read the next word, right? So it's hard to accurately measure this. I assume you could do some sort of experiments where you ask them to, I don't know, maybe rank a subset of words that follow any prefix. Maybe people have done this, I don't know. But if I find out, I will let you know on Piazza. But it's a good question, right? Because it's not like, humans obviously are not certain, and you can't be certain. Even if you have as much context as there is, there's still going to be uncertainty in almost every case over what the next word is, right? Do I decide to say bank or financial institution, or do I decide to, say there are many, paraphrases and just other things. So yeah, it's not like human perplexity is going to be the lowest that is possible. Yeah, not in this case. There are no human baselines for language models that I know of, at least. Yeah. Yeah, so calibration error here is referring to the fact that the shape of the distribution of these models might be not really what we want them to look like. And this is true in not only language modeling, but almost every task, as you say, in supervised learning. Our language models tend to be extremely confident on one or two words and have a very low probability of other words, even if they are somewhat plausible. And so, yeah, there are some papers I can share on things like this, but one of my actually the TA too, he's one of my PhD students. He's done some work on looking at the calibration of these models on various tasks and trying to figure out if the model confidence is a useful signal in these cases, but it tends to almost always be too overconfident.
Given that I was thinking these words are the people of classes.
Yeah.
So do we run into problems where we need like a giving by closing point per second to make sure that you're not messing around because like the probabilities can be like very tiny for some of the classes?
Yeah, I mean, we work in the log space. In general, that's not a big issue. Actually, we tend to use lower precision just because it's more memory efficient. So yeah, not a practical issue. Is there another question? Yeah.
So for the Engram models, do they by default use perplexity as the probability method, or do they have more?
Sorry, do they use what?
So just the count of percent is the only method to get Engram model?
Yeah. Yeah, so there are, I think maybe next slide. Yeah, so we'll get to that. The way to make these Engram models more sophisticated is by applying smoothing to them. So that's what we'll talk about for 3 minutes here. Okay, so one of the big issues with these Engram models is the fact that since they're based on counts, if I don't observe a particular bigram in my training data set, it will always have 0 probability. And that's not good because it's not like our training data set is going to cover every possible valid or even humanly plausible bigram in the language, right? And this also messes up our perplexity computation because if one of those things is 0, when we exponentiate like that, we get the divide by 0 error. So the question, how do we deal with these bigrams that are 0 probability? Actually, an example here, like Shakespeare produced 300,000 unique bigram types, and the number of unique words that Shakespeare used was like 30,000. So he could have produced 844 million bigrams, but of those, he only used 300,000 of them, right? So in the bigram table for Shakespeare's text, the vast majority of those cells are 0. He never produced these bigrams. And in many cases, that's legitimate. Like they might be ungrammatical, they might never be semantically plausible. But in other cases, those are valid bigrams that just weren't observed in the training data set of Shakespeare's plays. So as a concrete example, in our training set, we might have the phrases denied the allegations, denied the reports, and so on. In the test set, we observe denied the offer. We've never seen this before in our training set. Our probability of this is 0, and then thus the probability of the entire test set becomes 0 because we're doing this product of the probabilities. So I'm not going to talk about a specific smoothing algorithm. I'm just going to talk about the intuition of all smoothing algorithms, which is we have our training set estimates of these probabilities, and we have things that actually occur, right? Allegations occurred 3 times after denied the reports occurred 2 times, and this is in our training set. So we have 7 total instances of denied the appearing in our training set. So smoothing means we're going to steal probability mass from the things that we observed and then distribute it across things that we haven't observed. So for example, if I subtract 0.5 from all of the observed counts in my training data set, then I have two counts that I can distribute across every other word that could follow denied the in the bigram probability table. And the simplest way to do that distribution is uniformly. I'll just divide 2 by the number of words that have 0 counts in that row of the table, and I'll distribute that small amount of count across each of them equally. More complicated methods might not do that equally. They might pick words that are more likely to follow this particular prefix and then distribute more of that count to them. So there are much more intelligent ways of doing this smoothing, and this is how the Engram models get more and more complicated. Because smoothing actually helps quite a lot in terms of lowering perplexities, even after you count for the 0 probability problem, which even this simple thing does. Okay, wow, all right, so right on time. You have a couple things to look out for. Homework 0 is due on Monday. If you want to form a final project team, submit that Google form by September 15th, or we will randomly assign you to a group. Project proposal is due September 24th, and you're not going to have a quiz this week, but you will next week. All right, see you on Monday. Hi.
I had a quick question.
Yeah, sure.